The National Electrical Code requires receptacles to be installed at least 7 feet 6 inches above the finished floor or grade level in locations where water is likely to be present. This includes showers, bathtubs, and jacuzzi tubs. Fixed equipment, such as televisions, cannot be located within the 7 feet 6 inches clearance zone above the water level in areas where water is likely to be present. This also applies to small televisions mounted above jacuzzis. If it is possible, the receptacle can be moved to a location where the television can be placed at least 7 feet 6 inches above the water level on the opposite side of the wall. If moving the receptacle is not feasible, install a ground fault circuit interrupter (GFCI) near the receptacle. GFCIs provide additional protection against electrical shocks in wet areas. Instead of a fixed television, consider using a portable device such as a tablet or smartphone that can be easily moved when it is not in use. There are also specialized water-resistant televisions designed for outdoor use. These televisions can be mounted above jacuzzis without violating the NEC requirements. The applicable NEC article is Article 406.9, which covers receptacles in damp or wet locations. Article 406.9 of the National Electrical Code addresses the requirements for receptacles installed in damp or wet locations. This is crucial for ensuring electrical safety, especially in areas like bathrooms, kitchens, and outdoor spaces where exposure to moisture is common. Firstly, let's define what constitutes a damp or wet location according to the NEC. A damp location is defined as an area that is partially protected from weather and is subject to moderate degrees of moisture. Examples include some basements, some barns, and covered porches. A wet location, on the other hand, is an area subject to saturation with water or other liquids. This includes areas such as direct burial in the earth, locations subject to saturation with water or other liquids, and unprotected locations exposed to the weather. Receptacles installed in damp locations must be suitable for the environment. This typically means that the receptacle must be listed as weather resistant, often identified by the letters WR on the device. Weather resistant receptacles are designed to withstand exposure to moisture without corroding or malfunctioning. Receptacles in wet locations require even more stringent protection. The NEC mandates that receptacles in wet locations must be installed in an enclosure that is weatherproof, whether or not the attachment plug is inserted. This ensures that the electrical connections are shielded from rain, snow, and other sources of water, preventing short circuits and electrical shocks. Weatherproof enclosures are typically made of materials like plastic or metal that are resistant to corrosion and water ingress. They also feature gaskets or seals to create a watertight barrier around the receptacle. In addition to the enclosure, the receptacle itself must also be suitable for wet locations. This usually means it is a weather-resistant type, but it may also include additional features such as corrosion-resistant contacts and a sealed construction. When installing receptacles in damp or wet locations, it is essential to use appropriate wiring methods. The wiring must be suitable for the environment, meaning it should be resistant to moisture and corrosion. Common wiring methods for these locations include using cables with a moisture-resistant jacket such as Type UF underground feeder cable, or running the wires in a conduit system with watertight fittings. Proper grounding is another critical aspect of installing receptacles in damp or wet locations. The grounding system must be designed to provide a low impedance path for fault currents, helping to protect against electrical shock. This typically involves connecting the receptacle to a properly grounded metal box or using a grounding wire that runs back to the service panel. Ground fault circuit interrupters, GFCIs, are often required for receptacles in damp and wet locations. A GFCI is a device that monitors the current flowing through a circuit and quickly interrupts the power if it detects a difference between the outgoing and return current. This difference indicates that some of the current is leaking to ground, which could be a sign of an electrical shock hazard. GFCIs are particularly effective at preventing electrocution in wet environments because they can detect even small amounts of leakage current that might not be enough to trip a standard circuit breaker. The NEC has specific requirements for GFCI protection in various locations. For example, all 125-volt, 15 ampere and 20 ampere receptacles installed in bathrooms, kitchens, and outdoor areas must be GFCI protected. The GFCI protection can be provided by a GFCI receptacle installed at the point of use or by a GFCI circuit breaker that protects the entire circuit. When replacing receptacles in damp or wet locations, it is essential to follow all the NEC requirements. This includes using the correct type of receptacle, enclosure, and wiring methods. It also means ensuring that the receptacle is properly grounded and GFCI protected if required. It is important to note that the NEC is a minimum standard and local codes may have additional requirements. Always check with the local electrical inspector to ensure that the installation complies with all applicable regulations. The requirements outlined in Article 406.9 are designed to protect people and property from electrical hazards in damp and wet locations. By following these guidelines, electrical installers can ensure that receptacles are installed safely and reliably, even in challenging environments. Here are some additional considerations for installing receptacles in damp or wet locations. When selecting a location for a receptacle, try to choose a spot that is as protected from moisture as possible. For example, an outdoor receptacle should be installed under an overhang or in a sheltered area to minimize exposure to rain and snow. Be sure to use the correct type of enclosure for the location. A weatherproof enclosure is required for wet locations, while a weather-resistant enclosure is sufficient for damp locations. When installing a GFCI receptacle, follow the manufacturer's instructions carefully. Be sure to test the GFCI after installation to ensure that it is working properly. Periodically inspect receptacles in damp and wet locations for signs of damage or corrosion. Replace any damaged or corroded receptacles immediately. If you are unsure about any aspect of installing receptacles in damp or wet locations, consult with a qualified electrician. Working with electricity can be dangerous, so it is always best to err on the side of caution. In summary, Article 406.9 of the National Electrical Code provides detailed requirements for receptacles in damp and wet locations. These requirements cover the types of receptacles and enclosures that must be used, as well as the wiring methods and grounding requirements. By following these guidelines, electrical installers can ensure that receptacles are installed safely and reliably in any environment. Another key aspect of electrical installations in potentially wet environments is the appropriate use of ground fault circuit interrupters, commonly known as GFCIs. These devices are designed to protect people from electrical shock by monitoring the current flowing in a circuit and quickly interrupting the power if a ground fault is detected. A ground fault occurs when electricity escapes its intended path and flows to ground through an unintended conductor, such as a person. GFCIs are incredibly sensitive and can detect even small amounts of leakage current, typically around 5 milliamperes, and trip the circuit in a fraction of a second. This rapid response can prevent serious injury or even death. The National Electrical Code mandates GFCI protection in numerous locations where the risk of electric shock is elevated due to the presence of water or moisture. These locations include bathrooms, kitchens, laundry areas, garages, and outdoor spaces. Specifically, all 125-volt, 15 ampere and 20 ampere receptacles in these areas must be GFCI protected. The NEC also requires GFCI protection for specific equipment, such as dishwashers, swimming pool equipment, and hot tubs. There are two main types of GFCIs: receptacle type and circuit breaker type. Receptacle type GFCIs are installed in place of standard receptacles and provide protection only at that specific location. They are relatively easy to install and are a common choice for retrofitting existing installations. Circuit breaker type GFCIs, on the other hand, are installed in the electrical panel and provide protection for the entire circuit. They are typically used in new construction or when upgrading an existing electrical system. When installing a GFCI, it is crucial to follow the manufacturer's instructions carefully. The device must be properly wired and grounded to function correctly. After installation, the GFCI should be tested to ensure that it is working properly. Most GFCIs have a test button that simulates a ground fault and trips the device. This test should be performed monthly to verify that the GFCI is still functioning as intended. It is important to note that GFCIs do not protect against overloads or short circuits. These types of faults are handled by standard circuit breakers or fuses. GFCIs are specifically designed to detect and interrupt ground faults, which are a different type of electrical hazard. While GFCIs provide a significant level of protection, they are not foolproof. They are designed to reduce the risk of electric shock, but they cannot eliminate it entirely. It is still important to exercise caution when working with electricity, especially in wet environments. In addition to GFCIs, there are other safety measures that can be taken to minimize the risk of electric shock in wet locations. These include using properly insulated tools, avoiding the use of electrical appliances near water, and ensuring that all electrical equipment is properly grounded. It is also important to educate yourself and others about the dangers of electricity and the importance of electrical safety. By understanding the risks and taking appropriate precautions, you can help prevent electrical accidents and ensure a safe environment for yourself and your family. Grounding is a critical aspect of electrical safety, serving as a primary means of protecting people from electrical shock and preventing damage to equipment. It involves creating a low-resistance path for electrical current to flow back to the source in the event of a fault, thereby tripping a circuit breaker or fuse and quickly to energizing the circuit. The National Electrical Code mandates specific grounding requirements to ensure that electrical systems are installed and maintained safely. These requirements cover various aspects of grounding, including the grounding electrode system, equipment grounding conductors, and bonding. The grounding electrode system is the foundation of the grounding system. It provides a connection to the earth, which serves as a reference point for electrical potential. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. The grounding electrodes must be installed in accordance with the NEC requirements, which specify the size, type, and location of the electrodes. The equipment grounding conductor (EG) is a critical component of the grounding system. It provides a low impedance path for fault current to flow back to the source from metal parts of electrical equipment, such as enclosures, raceways, and motor frames. The EGC is typically a wire that runs along with the circuit conductors and is connected to the grounding electrode system at the service entrance. The NEC specifies the size and type of EGC that must be used for different circuits. Bonding is another important aspect of grounding. It involves connecting all metal parts of an electrical system together to create a common ground potential. This helps to prevent voltage differences between metal parts, which can cause electric shock. Bonding is typically accomplished by connecting metal raceways, enclosures, and equipment frames together with bonding jumpers or clamps. The NEC specifies the bonding requirements for various types of electrical systems. Proper grounding is essential for the safe operation of electrical equipment. It helps to prevent electrical shock, reduce the risk of fire, and protect equipment from damage. A properly grounded system will quickly trip a circuit breaker or fuse in the event of a fault, preventing a dangerous buildup of voltage. It is important to note that grounding is not the same as bonding. Grounding provides a path for fault current to flow back to the source, while bonding ensures that all metal parts of an electrical system are at the same potential. Both grounding and bonding are necessary for a safe electrical system. When installing or maintaining an electrical system, it is crucial to follow all the NEC grounding requirements. This includes using the correct size and type of grounding electrodes, EGs, and bonding jumpers. It also means ensuring that all connections are made properly and that the grounding system is tested to verify its effectiveness. If you are unsure about any aspect of grounding, consult with a qualified electrician. Working with electricity can be dangerous, so it is always best to err on the side of caution. Another vital concept in electrical safety is overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits and equipment from damage caused by excessive current flow. Overcurrent can occur due to various reasons, including short circuits, overloads, and ground faults. When an overcurrent condition occurs, the overcurrent protection device quickly interrupts the flow of electricity, preventing damage to the circuit and equipment. Circuit breakers and fuses are designed to operate in different ways. Circuit breakers are electromechanical devices that trip when the current exceeds a predetermined level. They can be reset after tripping, allowing the circuit to be restored to normal operation. Fuses, on the other hand, are single-use devices that melt when the current exceeds a predetermined level. Once a fuse has blown, it must be replaced with a new fuse of the same rating. The National Electrical Code (NEC) specifies the requirements for overcurrent protection in electrical systems. These requirements cover the selection, installation, and maintenance of overcurrent protection devices. The NEC mandates that overcurrent protection devices must be selected based on the ampacity of the circuit conductors and the rating of the equipment being protected. The ampacity of a conductor is the maximum amount of current that it can safely carry without overheating. The overcurrent protection device must be rated to protect the conductor from overheating and potential fire. The NEC also specifies the location and accessibility of overcurrent protection devices. Overcurrent protection devices must be readily accessible and located in a safe place where they can be easily reset or replaced. They must also be protected from physical damage and environmental conditions. Proper overcurrent protection is essential for the safe operation of electrical systems. It helps to prevent damage to equipment, reduce the risk of fire, and protect people from electrical shock. A properly designed and installed overcurrent protection system will quickly interrupt the flow of electricity in the event of an overcurrent condition, preventing a dangerous buildup of heat and potential hazards. It is important to note that overcurrent protection devices are not a substitute for proper wiring practices. They are designed to protect against overcurrent conditions, but they cannot prevent them from occurring in the first place. Proper wiring practices, such as using the correct size conductors and making secure connections, are essential for minimizing the risk of overcurrent. When installing or maintaining an electrical system, it is crucial to follow all the NEC overcurrent protection requirements. This includes selecting the correct size and type of overcurrent protection devices, installing them in the proper location, and ensuring that they are properly maintained. If you are unsure about any aspect of overcurrent protection, consult with a qualified electrician. Electrical bonding is a critical practice in electrical systems, ensuring electrical safety and proper system functionality. Bonding refers to the intentional connection of all non-current carrying metal parts of an electrical system to create a continuous electrical path to ground. This includes metal conduits, enclosures, equipment frames, and other metallic components. The primary purpose of bonding is to minimize the potential for electrical shock hazards. In the event of a fault, such as a short circuit or insulation breakdown, the fault current will flow through the bonding system back to the source. This low impedance path allows the overcurrent protection device, such as a circuit breaker or fuse, to quickly trip and interrupt the flow of electricity, preventing a dangerous voltage buildup on metal parts that could be touched by people. The National Electrical Code (NEC) outlines specific requirements for bonding in electrical systems. These requirements cover various aspects of bonding, including the types of bonding conductors, the methods of making connections, and the specific equipment that must be bonded. The NEC mandates that bonding conductors must be of sufficient size to safely carry the maximum fault current that could occur in the system. The size of the bonding conductor is typically determined based on the size of the circuit conductors. The NEC also specifies the types of bonding conductors that are permitted. Common bonding conductors include copper wire, aluminum wire, and metal raceways. The NEC also specifies the methods of making bonding connections. Bonding connections must be made using approved connectors and methods that ensure a reliable and low impedance connection. Common bonding methods include using bonding screws, bonding jumpers, and exothermic welding. The NEC requires that all non-current carrying metal parts of an electrical system be bonded. This includes metal conduits, enclosures, equipment frames, and other metallic components that could become energized in the event of a fault. Proper bonding is essential for the safe operation of electrical systems. It helps to prevent electrical shock, reduce the risk of fire, and protect equipment from damage. A properly bonded system will quickly trip a circuit breaker or fuse in the event of a fault, preventing a dangerous voltage buildup on metal parts that could be touched by people. It is important to note that bonding is not the same as grounding. Grounding provides a path for fault current to flow back to the source, while bonding ensures that all metal parts of an electrical system are at the same potential. Both bonding and grounding are necessary for a safe electrical system. When installing or maintaining an electrical system, it is crucial to follow all the NEC bonding requirements. This includes using the correct size and type of bonding conductors, making proper bonding connections, and ensuring that all required equipment is bonded. If you are unsure about any aspect of bonding, consult with a qualified electrician.